Hello, everyone, and welcome back. We are still on related rates. Don't know if that's a good or bad thing, but I find these problems quite interesting as they are very applicable to how everything is changing, how they're related. Because one thing changes, a lot of things change. A lot of things are related to each other in life. So this is an example that is one of the extra credit questions of this. Whether you choose to do it or not, but I know that it's a good example to show you a different way that a geometrical representation might be put together. Okay. Now, remember with related rates, you kind of want to remember these things is always draw a picture first, look at the geometry, and again, we want to use implicit differentiation before substituting in values. Substituting in your known values. That's kind of the way you want to go about it. And I know I spelled that wrong. Substituting. Yeah. You get the idea. All right, so here we go. Wine is poured into a glass seen below. And you do not see that below, but I'll draw it in a second. The glass is in the shape of a hemisphere with a radius of 3 centimeters. Wine is poured into glass where the height of the wine is changing by a centimeter per second. What is the rate that the exposed air of the wine is changing when the height of the wine is at a half centimeter? So what you should have saw here is we have a glass that has a hemisphere shape, okay, like so. Okay. And there's wine in it, something there. And we know that the radius is 3 centimeters. And what we also know in this problem is we know the wine is being poured in glass where the height of the wine is changing. So if I call this h, represent the height of the wine, we know that dh dt is equal to 1 centimeter per second. Okay. What is the rate that the exposed air of the wine is changing? So the exposed area is the top of what you're seeing. So the idea here to understand this problem is if we looked at an aerial view of this problem, if you looked down on the wine glass, what you'd see are, since it's a hemisphere, you'd see circles. And over time, those circles are going to get larger and larger as you pour more wine and it fills that glass. So we want to study is how is that changing over time. So what we're looking for here is we want what's the rate at which the surface area is changing in relation to time when the height is equal to a half. So that's what we're going to try to solve in this problem. Okay. Now, what's the geometry here? So we drew our picture. What's the geometry? Now, in the last problem, if you saw the last video, we had a cone. And in the cone, so if it were a cone, like so, what we're able to do is see similar triangles right here, where if I pull this picture out, because maybe I'm a little too small here, is we had a similar triangles, and where this was, the liquid down here, and then we could set up a proportion to relate the radius and the height. But we can't use this here because this is only if it's a cone. If we tried drawing that here, a cone would not represent the shape of this glass because this glass is curved like a hemisphere. So this is only for the cone. What do you do for the hemisphere is there's a little bit of creativity needed to see it here. But the right triangle you gotta create is from the top of the glass to the top of the liquid over to the edge of the glass where it's at. And there's your right triangle right there. And that's an accurate picture. If I pull this out, so you can see it, is we're gonna have a right triangle here. Now, what do we see from this picture though, is that since this is the radius of the wine. We don't know the radius of the wine. And the distance from the top of the glass to the edge of the glass, well, since it's a hemisphere, that's the same all the way around. That radius is uniform. So we know that this is 3 centimeters. And what we also know is that that entire distance from the top of the glass to the bottom of the glass is 3 as well, because it's a hemisphere. So that distance of the triangle, where we denote the height of the wine is h, that distance of the triangle is going to be 3 minus h. I'll label that over here on the picture over here. That'll be 3 minus h. So we can talk about rate and height in terms of each other here, and that'll help us when we do surface area. Because again, you might be asking yourself, why are you even doing all this, Mr. Hine? We want to find how surface area is changing. Let's just look at the surface area equation. And again, you could say, okay, surface area being a circle is going to be pi r squared. But since we're given the height, we need to talk about how this is changing in relation to height, not the radius. So we actually can't work with the formula as is. We have to do a little bit of work first. All right, so from our Pythagorean theorem, we would have that r squared plus 3 minus h squared is equal to 3 squared. And we want to get r by itself, so we can write this in terms of its height. So r is going to equal the square root of 3 squared minus 3 minus h squared. And I'm going to clean this up a little bit. I'm going to write r is equal to, that's going to give me 9. That'll give me 9. And then if you had another 3 minus h, it would be 9 minus 3h, you'd have minus 6h plus h squared. If I clean this up a little bit, I'm going to write this as 6h minus h squared. So we can plug that into our surface area equation. So the surface area, instead of talking about how its radius is changing, we can look at it in terms of its height, which, and this is, by the way, this is radius and height of the liquid, not of the glass itself. Okay. So then we have here that that's going to be square root of 6h minus h squared. Okay. And all of that's being squared since it's radius squared. So then what we'd have there is surface area is going to equal pi, and those will cancel, so you end up getting 6h minus h squared. Okay. Now, we can differentiate both sides with respect to time, and what we're going to get is the surface area is changing with respect to time is going to equal, now pi we can always pull in front, so we'll just bring the pi in front, and the derivative of 6h is going to be 6 dh dt minus, and then by the chain rule it's going to be 2, leaving the inside h, times the derivative of the inside, which is times dh dt. I don't know why I put that parentheses there, sorry. Oh, well, yeah, because all of this has a pi around it. There you go. Okay. Now, again, we want to know the surface area when the height was at 1/2 centimeter. So we can plug that in for h, and then we can more or less try to solve for dh dt. So what we get here is the surface area. Oh, wait, what am I saying? Solve for the dh dt. We're solving for the surface area, how that's changing in relation to time. And we know dh dt is 1. We know that already, sorry. So, get back to work and plug it all in. We're going to get pi. It's going to be 6 times 1 minus 2 times 1/2 times 1. And then cleaning this up a little bit, we'll see it's pi. 2 times 1/2 will be 6 minus 1. And your answer here is 5 pi, I believe. Make sure I didn't make a mistake anywhere. Yep, good. And there's your answer to this problem. So the surface area, when the height is at 1/2 centimeter, is changing by 5 pi, because its area will be centimeters squared per second. And there it is. Which you might think, man, that's a pretty large number, 5 pi, 15 centimeters per squared. But what you can think about is when it's 1/2 centimeter tall, I mean, the wine's going to be very small. And at the very bottom of a glass, it fills up quicker in the beginning, or at least the area from the top is going to fill up quicker than towards the end when it starts to slow down because the width of the glass is getting wider. Okay. So there's an additional problem. I hope you can kind of follow how that works. And if you try the extra credit your problem yourself out in relation to this, see how you do first before looking at the answer key or looking back at this, and use this to fill in any gaps. All right. Hope that helps, and I'll be available if you need any help during office hours or send me an email or message. All right. Take care, everyone. Bye bye.